Hi there, this video is going to walk you through setting up the total differential for enthalpy, or H, which we know is given by the expression H equals U plus PV. Now remember, U is that internal energy that we've been working with for a while, and then we just have this addition of pressure times volume. Okay, so we're going to start off by taking the derivative of this entire expression. So we will have dH equals du plus d of PV. Okay, so the one thing that we want to remember here is that we need to take the differential of this whole quantity. Okay, so don't forget to use your product rule. All right, so in that case, we want to rewrite this as du plus pdv plus v dp. Okay, so again, implementing that product rule. Okay, so remember that's your f prime g plus g prime f, if you've forgotten, is where we end up with this part of that expanded expression. All right, so now our next step is we can sub in what we already know about our internal energy, U. So we've spent some time with U, so we can plug that in. So remember, we know du is equal to CV dt plus pi t dv. So hopefully that looks familiar at this point. And then we can just plug that in to our equation up above, and we end up with CV dt plus pi t dv plus p dv plus v dp. Okay, so this is our general form of the total differential for enthalpy. Okay, so it looks like a mess. Let's not kid ourselves, but we will soon see that we can put this to some good use for us. All right, so let's take a look at how things can be adjusted for when we're talking about a van der Waals gas. Okay, so here's our equation from before that we just developed. That's our general form of our total differential for enthalpy. So we're just going to plug in what we know for van der Waals gas. So we know that our pressure is given by this expression, and we also know that pi t is given by this expression here. So we're just going to plug those in to our equation up top, and we end up with dH equals CV dt plus, I'm just going to put these in parentheses, we have pi t plus nRT over v minus b minus an squared over v squared dv. So all I've done there is to just pull out the pi t and the p that are both multiplied by the dv. And then don't forget we still have a v dp left there at the end. Okay, so remember we know that pi t is equal to an squared over v squared, so these will just cancel out. Okay, so we can simplify that total differential for the enthalpy, and that will look, when all is said and done, like this. All right, so this is our total differential for enthalpy for a van der Waals gas. All right, so you may be asking yourselves, why do we care about these total differential expressions? Well, it turns out that they allow us to calculate some pretty useful quantities. So the one example we're going to do here is to ask ourselves the question of, how does enthalpy change with pressure at constant temperature? Okay, so we have our expression for the total differential for a van der Waals gas for the enthalpy. And essentially what we're doing is asking ourselves, what is dH dP at constant temperature? Okay, that has a simplified notation, has a symbol of mu t. Right, there's no real interesting name for this quantity. It's not like what we had for pi t, which was internal pressure, so this just goes by mu t, and it represents the change in our enthalpy with pressure at a constant temperature. All right, so in order to get this quantity, we're going to simply impose the differential across the entire equation. Okay, so we're going to impose this derivative with respect to pressure across this whole expression. Okay, so what we'll do is we'll simplify things by assuming that we have 1 mole of our substance, so that will get rid of our n's, so we can just simplify things a little bit. So then we end up with dH dP at constant T is equal to CV dt dP at constant T plus RT over V minus B times dV dP at constant T. Hopefully you're getting the pattern here. And then we have V dP dP at constant T. Okay, so again, all we've done here is just to impose what we're doing to the enthalpy, okay, to the entire rest of the expression. Okay, so we want to take the derivative with respect to pressure at constant temperature, so we're going to do that for the whole expression. Okay, so continuing on here, it looks nasty, but we can simplify things quite a bit by applying what we call no-brainers. Okay, so if we think through these different terms, we can recognize, hopefully, that the change in pressure with respect to a change in pressure at constant temperature is going to be 1. Okay, and then also the change in temperature with respect to pressure at a constant temperature is going to be 0. Okay, so these types of relationships you want to look for in these expressions, because that will allow you to simplify things quite a bit. So what we end up with then is we can say that our dt dP at constant temperature is going to disappear. So that's going to be 0, right? Obviously no change in temperature at constant temperature. And then we have that dP at constant temperature. Here that is going to just go to 1, right? Basically 1 over 1. Okay, so that makes things a touch nicer. So we end up with our new expression for the change in enthalpy with respect to pressure, and we get RT over V minus B, derivative of V with respect to P at constant temperature, plus V, right? And then remember, again, this is all essentially allowing us to calculate that that quantity mu T. Okay, so this is our new expression for mu T. One thing that I'll point out is that this quantity right here sucks to evaluate. Okay, so you can't actually do that analytically, which is what we would like to do. All right, so you might be saying, well, then what use is this equation then? Okay, well, it turns out we have a trick to get around that nasty derivative that we don't want to evaluate, and it is called the inverter. All right, so this is the inverter trick. Okay, so we can just rewrite this expression here, our dv dp at constant t, by taking the inverse, so 1 over that, okay? 1 over the inverse, right, will be equivalent. Now, what is nice about the inverter is that this quantity here, dp dv at constant t, is something that we can evaluate pretty easily. Okay, so you'll have some practice with that on your homework, but let's just finish up with our new expression. So that leaves us with a new expression for mu t of rt over v minus b times, again, just plugging in that inverter expression, plus v. Okay, so that just nicens it up a little bit into something that is easier for us to evaluate. Okay, so again, the whole point of that inverter is this quantity is difficult to evaluate. We use the inverter here to give ourselves an expression that's easier to work with. All right, so you'll continue on going through this sort of proof on your homework. So just remember that you'll want to use your trick of a Taylor expansion when you do that. So remember your Taylor expansion, 1 over 1 minus x equals 1 plus x squared. Again, your assumption is that x is much, much less than 1, okay, in order for that to converge. So just remember that the trick in your homework problem is you need to decide which one of these terms in your denominator is the smaller one, and that's going to help your problem to work out correctly using that Taylor expansion trick. All right, so hopefully that helps you navigate through some of these equations, and I hope that was helpful. Thanks.